We're going to begin talking about hard problems. And in order to do that, we have to introduce the idea of a decision problem. The reason why is that usually when we talk about hardness, we talk about the hardness of a decision problem. We're going to introduce decision problems in the context of the shortest path problem. So we'll introduce the decision version of the shortest path problem. The difference between the shortest path problem and the decision version is just a small tweak of the input. The input for the decision problem is a graph, the weights on the arcs, the start node S and the terminal node T. But now we introduce an additional piece, which is our target objective function. When we talk about a decision version of a problem, we have some target in mind. Our output is now completely different though. In the shortest path problem, we generally output either the length of the shortest path or the shortest path itself. In the decision version of that problem, we output either yes or no. We output a yes when there exists an ST path that has a length less than our target length, and we output no otherwise. In this way, we're making a decision. If there is a shortest path and its length is less than our target, then we output yes. If there isn't a shortest path whose length is less than the target, then we output no. We've transformed a problem about shortest paths into a problem that outputs either yes or no. Solving a decision version of a problem is very much like solving an optimization version of a problem. We're going to be concerned with the running time of algorithms that solve these problems, and with this view, decision problems are more or less equivalent to optimization problems. This is because if we have a decision problem, we can use a reduction and solve the optimization problem. We're going to demonstrate that in the case of the shortest path problem. We'll take the decision version of the problem, SPD, and use it in a reduction to solve the optimization version of the problem, SPO. To make our lives a little bit simpler, we're going to say the weight of every arc is going to be equal to 1. In this way, a shortest path is really just counting the number of arcs that it's going to use instead of summing the weights of all the arcs it's going to use. Now we can talk about our reduction. Our reduction is going to use a counter. This counter is going to be I. It starts at 1 and is going to increase iteratively. Our algorithm is going to stop if our counter ever reaches the number of nodes, that is the cardinality of V. The way our reduction is going to work is, at a particular value of a counter, we're going to take the optimization version of the problem's input, copy it to the decision version of the problem's input, and introducing a target. The target is going to be the value of our counter, I. Then we take this input, which is now an input to the decision version of the problem, we solve it, and if we get the answer yes, then we say that the value of our shortest path, the optimization version of the problem, is going to be equal to I, the value of our counter at this time. The reason this is going to work is because we start our counter very low. The shortest the path could possibly be is 1. And the first time our counter gives us a value of yes, we know that that's going to be the shortest path value. We'll get a yes at this value of I and all ones above, but didn't get a value of yes for any value below. If, however, we end up at a particular value of I and we get the answer no, then we increment our counter to be 1 higher. We'll continue with this until our counter runs off of the end, that is it reaches the number of vertices. If we've reached the number of vertices, and our decision problem still says that there's no shortest ST path less than I, we know that there's no ST path, because when all of the weights are 1, the longest our shortest path can possibly be is n, going through every node exactly once. So there has to be no ST path. Now we can think of this algorithm as a reduction and talk about its running time. In this case, our counter goes from 1 to V. So we have order V runs of our algorithm. And every time our algorithm runs, it calls the SPD algorithm exactly once. So now we actually have executed a polynomial time reduction. We have some routine that uses the SPD problem as a subroutine, and it solves the SPO problem. We have a reduction. And better, it's even polynomial time. A reduction like this is achievable between any decision and optimization problem. We just have a counter and we continuously call the decision problem. This means that if we have a polynomial time for the decision version of any problem, we actually have a polynomial time for the optimization version of that same problem. The reduction we just solved, though, is not the one that's going to be more universally implemented. That was a linear search, and in general, a linear search isn't going to result in a polynomial time reduction. It just happened to in that one case. The general search strategy we're going to need is a binary search type approach. So now we're going to outline a binary search reduction technique between an optimization problem and a decision problem. In this binary search technique, we're going to consider, again, the weight of every arc being exactly equal to 1. We're still focused on the SPO problem and the SPD problem. The binary search routine is going to keep track of two values, a lower bound and an upper bound. The lower bound is going to be a lower bound on the value of our shortest path, and the upper bound is going to be an upper bound on the value of the shortest path. In this case, we started with a lower bound of 1 and an upper bound of n. If the upper and lower bound ever meet each other, we terminate the algorithm. But until that happens, we run an iterative loop. In this iterative loop, we find a target value, t. In this case, our target value is going to be between the upper bound and the lower bound. And because we'd like our target to be an integer, in this case, we've taken the floor. Given this target value, we input it into the SPD problem and run our algorithm. If we get that the answer is yes, that is, there is a shortest path of value at most t, then we update our upper bound to be equal to t. Now we know that there's going to be a shortest path that's at most our upper bound, which is our target value t. If, however, with this new target value, we run the SPD algorithm, we get the answer no, then there is no shortest path that has value at most t, and so we update our lower bound. All shortest paths have to have a value larger than t. At the conclusion of our algorithm, our upper bound and our lower bound are going to be the same. And at this point, we know that the value of our optimization problem is going to be equal to the value of our upper bound, or equivalently the value of our lower bound. This binary search technique actually has considerable time savings over to the linear search technique. Specifically now, we only have order log of the number of node calls. This is because every time we increment our t value, we've actually cut off half of the values instead of just cutting off one value like we did in the linear search. If we actually analyze the runtime in a more formal way, we would get that the running time actually has order log v calls to SPD. So this is again a reduction, but now a very fast reduction. And in general, the binary search technique is going to allow us to convert decision problems into optimization problems in a polynomial time way. So now to summarize what we know about decision problems, in order to create a decision problem, we introduce a target objective function. Once we do this, we know that our optimization version of the problem can be reduced to the decision version of the problem. And so in terms of running time, they're generally equivalent. We can do this for any optimization problem. Every optimization problem has a decision version. The reduction we've seen in the binary search technique. We take the input to our optimization problem, we introduce a binary search routine that uses the decision as a subroutine. Afterwards, this results in an output to our optimization problem. We're going to use these tools when we talk about hardness of problems.